In this video, I'm going to be going through some practice problem calculations of dynamic head and pressure. So let's go ahead and let's get down to business. Two resources I want to point out here for you all that'll be very, very helpful is the actual engineering formula sheet. So if you click on that, it's going to end up bringing up the formula sheet here. We want to be navigating to section 16, which is water supply. These are two very, very important equations here, not only 16.1, but also 16.2. This has the dynamic head equation as well as the static head equation. Remember, anytime that we're talking about head, that's going to be the unit of feet of water. If we want to convert this to either static pressure or dynamic pressure, we have to take our value of the static head, divide that by 2.31, so that we could get static pressure. If you want to get dynamic pressure, you'd have to take dynamic head and divide that by 2.31, so that we can get it to dynamic pressure. So that basically what we're doing there is we're converting from feet of water to PSI. If you end up looking on here, you can type in feet of water. And so as you can see here in section 6, these are our conversions. 1 PSI is equal to 2.31 feet of water. And so that's why we're actually dividing by 2.31. It's just our conversion factor. So I'm going to go ahead and go back down to section 16 here so that we got that up and ready. But what I want to do is just, let's go ahead and go through these equations, these resources that we're going to be using. So this is the Hazen-Williams formula. And so just as we were talking about in class, if we took a ball, right, and we ended up rolling that on the ground, we give it this initial velocity, but what ends up happening is as it continues to travel, it ends up interacting with the surface that it is rolling on, right? And that surface provides friction, right? That's going to slow that ball down. It's exactly the same case for water as it's rolling through a pipe. The pipe's surface is not actually extremely flat or extremely perfect. If we zoom in on that, there's imperfections, right? And so those imperfections the water's going to interact with, and it's going to actually slow the water down as it's moving due to friction. And so the Hazen-Williams formula is this formula that we can use to determine what the head loss is due to friction as water is flowing through a pipe. Now this unit that we're going to end up getting is going to be in feet of water. So head loss is going to give us a unit of feet of water. There are many factors that are going to contribute to how much head loss actually occurs. So for instance, we have L here, that is the length of the pipe, and so that is in feet. Keep in mind, if you ended up getting a value in miles for your total supply line length, right, we would need to convert that to feet. So to go from miles to feet, you can find that in your equation sheet, but most of y'all probably know that it's 5,280 feet is in 1 mile. So if you have some value in miles, just multiply that by 5,280. We're also going to have Q, which is the flow rate of water. So that's in a unit of gallons per minute. Keep in mind, we've been seeing Q a lot, right? Now the variable Q is just always represented for anything that is a flow rate. So let's kind of recap. We had Q equals CF/CIA. That was the last time that we saw Q. Q in there was our, Q equals CF/CIA. That was for stormwater runoff. And so that was the flow rate of water exiting a property, right? We also had the heat loss, heat gain analysis that we had done. So it was Q equals AU delta T. So that was the flow rate of heat, right? Inside or out of a building. So Q in this particular case though is the flow rate of water. So it's how many gallons per minute. So how many gallons of water is going through this pipe per minute. We also have C, which is the Hazen-Williams constant, and so that is based off of the material type, right? Just like, if you remember, we were doing the stormwater runoff, Q equals CF/CIA. C in that case was dependent on the material type, right? We had different C values for forest land, for neighborhoods, etc. It's basically the same case here for C, except it's going to be different materials, right? So it's these pipe materials down here. D, remember, is the diameter of the pipe, and that is in inches. And so what we're going to do is we're going to get all of these values, then we can plug them into this formula to determine the head loss due to friction. Okay? Now, Hazen-Williams constant, C. To find that, we've got to look at this table here, just as we talked about in class. There's the pipe material down here, so you'll find out which material corresponds to your problem, right? Or your problem's going to say some specific type of material the pipe's made of. We're going to look at that row. If they end up specifying, hey, it's a clean new pipe, right? So maybe it's a clean new cast iron pipe, you'd use the value of 130. If they don't specify that, we're just going to end up using the typical design value. So in this case, if they just say it's a cast iron pipe, great. C value for that is going to be 100. All right. Last thing that I want to point out here in our resources before we start cracking down on some problems is the equivalent length in feet of pipe. Now, what is the equivalent length in feet of pipe? For our Hazen-Williams formula up here, we have to use straight pipe, right? And so it's just the length of straight pipe in here. What engineers ended up doing is they basically found for all of these fittings, whenever water is going through piping and it goes through a fitting, it does end up losing energy, right? As you all could imagine, you go through a 90-degree elbow, it's going to lose some energy. Now, what scientists and engineers ended up doing is they basically ended up finding out, okay, well, the amount of energy that is lost from this water going through this pipe, what is the equivalent length of straight pipe where we would lose the same amount of energy, right? So what they ended up doing is they found for like a 10-inch diameter pipe, if you go through one regular 90-degree elbow with 10-inch diameter pipe, the amount of energy that is lost is equivalent to the amount of energy that is lost if water is traveling through the same diameter pipe and it's just straight for 14 feet. Okay, so that's what the equivalent length is. So we're going to be using this table as well. Last thing I want to point out here before we crack down on some of these problems is we're going to end up uploading a picture of your work for the assignment after you are completed. I'm going to be showing you all how to document your work really, really well. You want to make sure that we're documenting every single step of the calculations, but also additionally that we're including units with our answer as well, and that we want to inbox the answer. All right, so without further ado, let's go ahead, let's get down to business. And so question number 2 here, we'll put up at the top here, Q number 2. So it says if your static head is 110 feet of water and you end up with a head loss of 4.47 feet, what would the dynamic head, or what is also known as the actual head, be equal to? So they want us to round our answer to the nearest hundredth place. Remember that all these answers will also accept up to 5% error for these. So let's go ahead, let's pop up here and let's get to our formula sheet. So I want to bring that up in here. Now, what section are we going to be looking at? If we scroll down, we can end up seeing water supply. It's section 16. And so in here, we'll find any important equations that we're going to need to know. The equation that we're using here is going to be the dynamic head formula. And so if we go on here, we can see that the dynamic head, equation 16.2, dynamic head is equal to static head minus the head loss. So now, what is the static head? What is the head loss here? If we end up going to this, we can see that the static head is 110. So 110 feet. The head loss that was calculated out for us is 4.47 feet. So all we've got to do here is to find the dynamic head. We've got to subtract these two numbers. If we bring out the good old calculator, we got 110 minus 4.47. Now, if we end up doing that, we are going to end up with a value of 105.53, and then that's going to be feet of water on there, okay? So that is the value that we'd end up with for this, so we're going to put in 105.53 there, all right? Now, moving on to question number 3. They end up asking us in question number 3 for the dynamic head. So they say the dynamic head is equal to, and let's bring this guy out here. Okay, so dynamic head is equal to 152 feet of water. They want us to calculate out the dynamic pressure. All right, so this is the actual head equal to 152 feet of water. And then also the dynamic pressure is what we want to solve for. So we've got on here 152 feet of water. And what we want to do is we want to convert that, right, to actually be dynamic pressure. And so instead of it being feet of water, we want it to be a unit of pounds per square inch. And so what we can do here is we can multiply this by a conversion factor. Now on the bottom, we're going to have the feet of water. At the top, we're going to have PSI. Now in 1 PSI, there's a certain amount of feet of water, right? And if we go to our equation sheet, what we can do is we can type in Control F, we can do PSI. And so if we end up going on here, we'll end up seeing in terms of pressure, it says 1 PSI is equal to 2.31. So 2.31 feet of water. These units are going to cancel here, feet of water, feet of water. We're going to be left with a unit of PSI, which is what pressure is, the unit for. And so now if we end up bringing up our good old calculator here again, we got 152, divide that by 2.31. And so now we're going to end up with 65.8 PSI here for this value. Okay, so we can move on to question number 4 next. We ended up putting in our answer there for question number 3. We're moving on to question number 4 now. So question number 4 is asking us, prompting us, what is the equivalent length of a 10-inch diameter pipe that has times 4 regular 90-degree elbows, and then we also have 1 branch flow T. Okay, so they're asking us what is the equivalent length equal to. So that's what we're going to be solving for, which is just EL is what we're going to say. This is going to be 4 times whatever value we end up getting for those regular 90-degree elbows for the 10-inch diameter pipe. So I'm going to put that in parentheses. And then we're going to also do 1 times whatever this value is for the branch flow T. So if we pop up here for question number 4, we can end up seeing on here the flange fittings. And so this is directly from our equation sheet as well. Be very, very careful. I'm going to actually bring this up on the equation sheet. So we want the flange fittings. This is a very common mistake that students will make on the EOC, is that they end up seeing the screwed fittings at first. We always want to, by default, go to the flange fittings. And so that's good that we're bringing this up and bringing that to your attention. So in terms of this diameter of this pipe, we've got 10-inch diameter pipe. Now we have 4 regular 90-degree elbow fittings on there. So if we scroll over here, we're going to have 14. And so we're going to take 4 times that 14, because they're basically saying if you run this water in a 10-inch diameter pipe through a regular 90-degree elbow, it's basically going to be the equivalent amount of energy that's lost of just water traveling through 14 feet of a straight pipe. So we're going to take 4 times 14. Then we want to add on the 1 branch flow T equivalent length. So if we end up scrolling over here, we can find that branch flow T, and so it's right here in this row. If we go over, that's going to be 30 feet for the equivalent length. So basically what that's saying is if you go through 1 branch flow T with 10-inch diameter pipe, that's the equivalent of the amount of energy that's lost just going 30 feet of straight pipe. And so now what we can do is we can end up calculating these out. And so 4 times 14 is going to end up giving us 56. 56 plus 30 is going to end up giving us 86. And then that final answer will be in a unit of feet. So we've got 86 feet here. And so what we can do is go ahead and pop down here for question number 4. We're going to put in there 86. And so remember, we just want the numerical answer. However, on our work, we always want to end up providing the unit. So that's the answer for number 4. Let's go ahead and let's move on to question number 5 here. So question number 5 reads, suppose your water supply line that you have determined a static head value of 495 feet and a head loss of 2 feet. They want us to determine what the dynamic pressure or the actual pressure would be for this. So in this case, remember, we want to look at dynamic head. And so if I end up searching for dynamic head here, it's thermodynamics, we now have this as dynamic head. Dynamic head is equal to our static head. So dynamic head is equal to our static head minus our head loss, right? Now, notice this is dynamic head, right? This is not dynamic pressure. What we're going to have to do at the end is this value is going to be in feet of water. We're going to have to convert this to PSI, right? So we're going to take this number divided by 2.31, whatever we end up with here. That's going to get us to dynamic pressure. So the static head in this case is equal to 495 feet of water. We're going to subtract the head loss, which is 2 feet of water. That's going to end up giving us 493 feet of water. Now remember, that's the dynamic head. For dynamic, or the actual pressure, right? So dynamic pressure, actual pressure, we want to take the dynamic head and we want to divide that by 2.31, which means we're going to take 493 and divide that by 2.31. So 493 divided by 2.31, we're going to end up with 213.42 pounds per square inch. And so that's going to be our dynamic pressure there, or our actual pressure. So let's go ahead and put that in, 213.42 psi. Perfect. So that basically brings us to our conclusion of these practice problems here. Hope that was helpful. If you have any questions, please do feel free, drop them in the comments. Would be more than helpful, or more than happy to help out. Happy calculating. See you all in the next video. Bye-bye.